get started?
Yeah,
Okay, everybody. Welcome to Secure Hardware Design. My name is Ravichandran. So I don't know if I've met all of you yet, but so who am I? I am one of the former TAs for this class. Help out with the Yuhang and the core staff here this year. So I'm the person to blame if you don't like your labs. So I designed roughly half the labs in the class. If you don't like Spectre or whatever, I'm the guy to blame. But you're going to love Spectre. It's going to be great. So first thing I want to do is just congratulate all of you on a job very well done with the most recent lab. So we know cache attacks is not the easiest lab in the world. I'm sure many of you spent many long nights on this problem, as we all did when we solved it. We think this lab is very valuable because it actually gives you such a rich exposure to the nature of what we do. So the experience you just went through is very much the stuff we do every day in our research. A lot of it is, why does this not work? Why is this set the one that's very active? Who knows? So hope you enjoyed it. I know it might have been tough. You guys did really, really great. So good on you for the hard work, and we really appreciate all of you guys. So with that being said, let's talk about physical attacks. So I want to start with a question here. What's a computer? You guys are all master's students or upper level undergrads in computer engineering, so you should be able to answer this. Come on. So what's a computer? Anybody? Yes?
It's this big box that does a lot of computation really quickly.
A big box that does a lot of computation really quickly. What was your name?
Joe.
Joe. Excellent name. Big box that does a lot of computation really quickly. I like that. Anybody else? What's a computer? You think computer, what do you think? Yeah?
Kind of a programming, any sort of programmable object that you can sort of configure to do different kinds of things.
Programmable object that you can configure to do different kinds of things. What was your name?
Nathan?
Nathan. So that's a great answer. I love that answer. So it shows this notion of the thing that can be reconfigurable. It can be general purpose. Anybody else? What's a computer? Yes?
A system that produces an input-dependent output.
A system that produces an input-dependent output. I love it. Remind me again your name?
David.
David, that's right. So you guys had some great answers about what a computer is. And so I'm going to take a little bit of a more, I guess you could call it, etymological view of what a computer is. So we're going to break a computer up into three main parts here. So it's a processor, like David said, it's something that takes input and processes to give us some output. It's also got memory. So like what Nathan said, it's got this ability to kind of remember and change its state. And it's got storage as well, so it can have this permanent storage aspect. So three parts to a computer: the processor, the memory, and the storage. So I want you to keep that in mind as we talk about physical attacks today. So here, what we have on the desk, we have many things on the desk, but one of the things we have on the desk right here is actually the most popular router on Amazon. It's the TP-Link WR841N. You go on Amazon right now, this is one of the best sellers. And we're going to ask the question, what's inside of this most popular router on Amazon? So let's go ahead and pop the lid off and find out what's on the inside. So here's some photos I took of the inside of the router. You can see we have some chips and some circuit boards and things. And here's a high-level view of it. And I want to ask you guys, when you look at this photo here, what do you see? What sticks out to you? Anything? Yes?
There's two jumper wires that somebody put.
Two jumper wires and something. Excellent, excellent point. So these are part of the antenna. So I'll show you in a second how these route, but that's actually, we did add some jumper wires, but those are not the ones that we added. But great observation. So we have some wires that are soldered to the board. Those are kind of weird. What else? Yeah?
It looks like a processor in the middle and some sort of memory that's stored on the left.
Okay, so we got a processor in the middle and memory on the left. Excellent answer. So you got two of the three things I was looking for. Did anybody find the last thing? What else do you see here? Yeah?
Did you manually add those LEDs?
No, so those actually come with it. You can see they're blinking right there.
Okay.
But yeah, that's just, I guess, the indicator lights. But good observations. We got some LEDs too. We got some different I/O that's not part of a traditional computer. So notice they use the word computer, not router. So I'll give you a spoiler here. The third thing is this SPI chip right there. So that's your storage chip. And so as we pointed out, we have a CPU in the center. We got some memory, so that's our memory element. We have some permanent non-volatile storage on the SPI chip. So if you look at what we talked about a computer is, these elements that we found on this circuit board inside of this router actually match up exactly one-to-one with what we said a computer is. So what we have here is not just a router, it's a general purpose computer, right? And so since it's a computer, it can be hacked, just like the ones we've been hacking in labs. So I want to come back to this image here really quick. There's actually one more thing that I was hoping someone might point out that no one caught. But it's these 4 little pads up here. These are kind of suspicious, right? What are these holes up at the top doing? You see they're labeled with some different labels, and we'll get a closer image here. So we have VCC, GND, RX, and TX. And it looks like these were put here intentionally by the designers as a breakout board for us to be able to, or for someone to be able to attach to. So I'm actually going to go ahead and write those down here, so we'll see these come back in a minute. We have VCC, ground. I'm guessing that's what GND means. I guess it could not mean that, but we're going to take an assumption here. We have RX and TX. Go ahead and lift that up so everyone can see. So those are our 4 pins here. And so for today's first of 4 demos, we're going to find out what happens when the vendor simply leaves the back door open. And so what we're going to do is we're going to try something a little different here. So I'm going to hop into spatial computing, and we're going to go ahead and take a look at what's on this chip, and you'll be able to see exactly what I see. So go ahead and mirror here.
It's not an advertisement, for sure.
Yeah, I wish I had $3,500 to that for it.
So let's see if we can go ahead and mirror. And you guys will be able to see exactly what I'm seeing, so I'll be able to point out to you. Yeah, it's the...
Yeah, that's the video.
It's just the tax write-off.
All right. So you guys can all see yourselves here. Hello. And we're going to go ahead and sit down. So let's take a look at what's on the desk. So we have a couple things here. Is everyone able to see what I'm looking at? Oh, all right. So we have a couple things here. We have, first is the oscilloscope. So this right here, everyone can see that? This is an oscilloscope. This is used for measuring voltages over time. So you can actually plug in different probes, like I'm going to do here. And this probe is now attached to the scope, and we'll be able to see what voltages are present on this wire. Okay, so the next thing we have, I guess I'm too close to this place here. We have the router that I was talking about before. And you can see here that I've gone ahead and connected these extra wires right here. Did everyone see that? We have these wires that have been soldered onto those pins. And I brought the wires over here to this breadboard, which we have some other things we can connect to. So we can see what's happening on those pins. I'm just going to show you while we're in spatial computing here what else we have. We have 2 other boards here that we're going to do a demo on later. This one is going to be used for power analysis, and this one is for fault injection. So we'll come back to those in just a minute. But that's what I have on the desk here. So, any questions? All right. So that's what we got on the desk. Now let's go ahead and plug in and see what happens on the scope when we plug into one of those pins. Like that?
You can attach to outside of it.
Oh, got it. Smart. All right, is that better? Cool. Okay, so we got our router here. Maybe I'll take this. Is there like am I missing something?
Oh, so last time when the student give a presentation, as long as they stay closer to the mic will just get
Yeah, we
the
can
sound.
use that. Just throw this guy here.
So you
Actually,
can
maybe,
mute-
is that-
We can mute it, and
Okay.
then you can just talk here.
Got it.
Okay. It
All right.
will capture.
Cool. Okay, so what I'm going to do here is go ahead and connect the oscilloscope to the pins that we have broken out. So we have 2 pins here. We're going to go ahead and plug into one of them. Let's just see if we see anything interesting happening on the board here. So what we have on the screen is the actual output of the voltages on those pins. And as you can see, it's kind of relatively straightforward, except every once in a while, it seems to fluctuate a little bit.
Are you the RX and TX pins?
Yeah, exactly. So to be specific, we're plugged into the TX pin. You should see something. This is the beauty of live demos. So yeah, there we go. So we got some twitching going on of some kind. I'll go ahead and bring this up. And let's see if we can see what's being sent here. So clearly some data is being sent to this line. And so what I'm going to do is zoom out for us and set up a trigger so that when the voltage spikes, it'll actually capture that signal for us. And you can see, okay, we've just got some data here. So this is clearly some type of data, some type of communication. You can see we're going from 0 to 1 up and down. Right? So let's see if we can figure out what this protocol is and what's being sent on the wire. So I'm going to zoom out even more. I'm going to wait for it to capture some data. And so you can see we just caught some data right here. Everyone can see that? We got some nice traces here. So let's go ahead and decode this. And so I'm going to do a little bit of an educated guess here. And we're going to hop into the decode mode. And we're going to guess that this is a protocol called UART. And so we're going to go ahead and identify our signal here with a threshold. We'll throw a threshold value right here between those zeros and ones. We'll say that's around halfway between the 0 and the 1 condition, right? And we'll go ahead and display what this is being decoded as. So if we treat this data as ASCII hex data in an 8B1P, an 8-bit 1 parity bit encoding, which is a very common encoding scheme, if we zoom out a little bit, you can see we actually have some text data being sent. We have the string NTP start 504 NTP something something. We have some data here. So we found a port with some actual data being sent from this router. So let's go ahead and connect in what's called a UART adapter and see if we can talk to the router. So we've been able to receive what's on the router. Let's see if we can inject some data. And so here I have what's called an FTDI chip. This is a UART adapter right here. Can everyone see that? No, it's kind of hard to see. Move it up a little bit. So this guy is able to talk this UART protocol. So let's go ahead and plug this in and see if we can get some data being received. Okay, got it. Look here? Okay, try. I just don't want it to start like clicking. Okay, so let's go ahead and connect this in. We'll see what happens. And so I'm now connected into the serial port. Let's just wait a second to see if that data comes back. And I'll bring the scope here too.
What is adding to casting?
I'll talk about that in a minute. So you can see we have that data. We have this NTP connect failed return stuff that we saw before. So we're able to read the data that was being sent on those lines. You can see we actually have a live view of the data being sent on the oscilloscope, and we can also see what's going on here. So I'm going to go ahead and add on a pin to this TX pin and see if we can actually send some data. So let's go ahead and add another probe. And we're going to probe that other pin, this TX pin. And so now what I'm going to do is actually configure the oscilloscope to watch for those UART transactions and stop when it sees one. So this is a thing you can do. Instead of doing edge triggering, we're going to do a serial triggering. And this is just like a known pattern. So we're going to select our protocol as UART. We'll talk about what UART is in just a second. But that's the protocol that's being sent here. We'll configure our TX pin. And we'll go ahead and run it. Zoom out a little bit. And if we go ahead and try to send some data here, you can actually see we're observing transactions on the bus. And so we're able to actually input data and observe the contents over the serial port. But now let's see, what are we actually looking at here? So whenever I press enter, I can see a little shell sign. What does this remind you guys of? This looks to me like a shell. And so if I go ahead and type something like echo user, oh, I'm the root user. That's pretty interesting. So it seems like this router is just giving us a root shell completely for free. So let's see what else we can do. If we pop into here, we can actually ls, and oh, it's a Linux system. We can go into proc, and we can see we run a MIPS processor. We can use CPU info. You guys should be familiar with that from the labs. And you can see we're totally root on this Linux system. So we have complete ownership of this router just by plugging into some pins that were already on the router. So any questions? Yes?
Wait, so do most manufacturers just have these like TX and RX pins just like publicly available, I guess?
You would be shocked how many people do this.
I see.
Any other questions? Okay, so what? Oh yeah.
What if the OS is not a Linux that we can use this to talk to, or the protocol is not a well-known one that we can just guess?
Excellent question. So in this case, we were able to just guess the protocol. Like I said, it's a very common protocol, so I was able to guess. If you didn't know what the protocol was, you'd have to do more reverse engineering. But you'll find, I'd say 9 times out of 10, it's going to be this type of 8B1P encoding on UART. So let's talk about UART. Let's see what we're looking at here. So we have those pins, those UART, those TX, RX, and ground pins. So this is something called UART, Universal Asynchronous Receiver Transmitter. And the idea here is that every device is going to have a transmitter pin and a receiver pin. So TX is for transmitting data, RX is for receiving data. And the idea behind UART is that it's asynchronous. So every device is going to pull these pins at a regular interval. So you notice when I connected, I specified the number 115200 as an argument to the screen command. That's actually the baud rate, the actual rate at which we're going to pull these pins. And so to use this UART adapter, you have to specify the frequency. How would you be able to learn this frequency? Well, you could use the oscilloscope. Like we saw, we can actually look and see how these timings are being sent, or you could guess. So the one that I guessed is the most common for routers. So that's a brief look at UART. So what other interfaces are out there? So you asked earlier, what else can we find? So UART's a very standard one. It's a serial protocol. You'll find it on most devices. There's also I2C or SPI. So earlier we saw that SPI chip for that non-volatile flash. You actually, when your PC BIOS starts up, it uses SPI. And so one thing, if you want to see more, you can actually come to Office Hours and we'll show you. We got a PC in the lab that we actually attached a debugger to, and we were able to dump the SPI flash from the BIOS and reflash it and modify it with our own BIOS image. And so you can do kind of crazy things like that with SPI. The other thing you can do is something called JTAG. So I have here what's called a J-Link. So this is a J-Link JTAG adapter that you can use to plug into JTAG. And if you can get access to JTAG, you get access to basically anything you want on the CPU. So you can debug the CPU, you can dump firmware, you can rewrite the memory, you can do whatever you want. So JTAG is very, very powerful. It's really, really fun. If you want to see more, come to Office Hours. We can show you some more toys and some more fun things. So that's a brief look at the UART protocol and some very simple ways to get into systems. Now let's take a look at the overall iceberg of hardware security. So up in user space, this is where you guys have been in your first labs. We've been in user space. It's very clueless. You don't know what's going on. You're just kind of talking to the operating system. And so beneath you is something like Linux, where you can do system calls. So in lab 1, you might have used some system calls to talk to the browser to see what the time is or whatever. And so the user space is able to talk to the operating system through a very nice interface, a relatively clean interface. Then you have the kernel, which is beneath the operating system, and things get a little bit less fun down here. So this is where you're actually interacting with the ISA and doing things like local descriptor tables and all that nonsense. And if you know what that is, I'm very sorry. Beneath the ISA, you have the microarchitecture. So this is what we spend a lot of our time attacking in this class, right? This is things like the branch predictor or your caches. And then beneath even that, we have physics and analog signals. And this is the weirdest region. So this is what we're going to spend our time on today, this analog world. So there's 2 types of physical attacks we want to talk about. The first is called active. So an active physical attack is where you're actually going to inject your own signals into the chip. So this would be something like we just did. We sent some data to the chip. That's an active attack. With a passive attack, you're not actually changing the chip's behavior. You're simply monitoring the chip to see what is it going to give you. Is there any side channel leakage? Is there any physical phenomenon you can just observe passively? So active and passive, those are our 2 flavors. And so I wanted to kind of plot out some of the different attacks that people can do against these chips. And so on the x-axis here, we have the level of invasiveness. On the y-axis, we have the expense. And so we'll just list off a couple common hardware attacks and just plot them against this plot here. So my personal favorite, I think the coolest thing you can do is this thing called a focused ion beam. And so this is actually used a lot in like material science research and metallurgy, where you're able to actually inject directly into the silicon, modify the silicon itself. So it's a very expensive machine. These are really, really cool. If anyone happens to have one, let me know. I want to come play with them. But they're very expensive and they're very invasive. So these are very difficult to use. We also have things like optical imaging. So this is less invasive. You're able to just take pictures of the device, but depending on how accurate your camera is and how much optical detail you want, this can get really expensive. There's also laser etching. So the idea with laser etching is you're going to actually etch into the chip with a laser to change different things. For example, like you might want to change a fuse, for example. Next is decapping. So we have these chips. You've probably seen some chips around. We just saw some chips. Actually taking them and decapping them. So taking off that epoxy layer to unveil the silicon beneath it. That's chip decapping. Really cool stuff. There's power tracing. So this is kind of in our sweet spot of cheap and non-invasive, where you're able to observe the power trace of the chip and see, okay, if the chip's using this much power at this time, you can infer the behavior from the chip. There's fault injection, where you actually maliciously try to inject faults into the chip to make it do things it's not supposed to do. And logical interfaces, like we just saw, like UARTs or JTAG or SPI. So that's kind of your roadmap of hardware security attacks. And you'll notice there's this general trend where things tend to scale up. As they get more invasive, they get more expensive too. And so today we're going to focus on these three things down here because we like cheap things. So we have the cheap stuff that's not super invasive right here on the desk. Any questions on the overall? Yeah, Fisher.
Yeah, what can you do with optical imaging?
I actually have a slide on that, so we'll show you in a second. Yeah.
Once you decap to get the silicon, can you actually infer anything from it?
Infer anything?
Like, can you like infer the architecture from it?
I have another chip, a slide on that too, so we'll show you in a second. Cool. So you just asked what does it look like when you take the cap off a chip? This is the inside of a chip. So in case you've never seen before what's inside of a chip, this is your actual silicon substrate. So you can see we have these wires that are bonded onto the pads, and this is the silicon of the actual chip itself. So if you were to successfully decap a chip, this is what it would look like. So here's some more photos of decapped chips. So you can see we have full exposures of the silicon. You can actually read back, take photos of the silicon, try to reverse engineer it, do things like that. This is actually a photo of me in the lab doing hydrofluoric acid etch of some real silicon. And that's very cool if you've never done silicon fab. Hydrofluoric acid is very, very scary. But this is actually how you can etch chips, and part of the manufacturing process is you use hydrofluoric acid to eat away some of the oxide layers. And so here's another photo of what optical imaging might get you. So this is a laser scan of some SRAM. You actually see visually that if you scan the chip while it's in action, you can kind of read out some of the bits. You can see what the state of the SRAM is just through optics alone. And here's another photo of some layout of those SRAMs just from a VLSI perspective of what the chip might look like. So you can do a lot of really cool things with physical access to chips. So in this class, we're going to do 4 very cool things. We have 4 attacks we're going to do for you. The first is UART, which we've just seen. The second is fault injection. Next is power analysis. And finally, timing analysis. And so you can kind of classify these chips into 2 different domains. The ones on the left are active, we're going to inject stuff. The ones on the right are passive, we're just going to monitor stuff. And so we just did UART. Let's move on to fault injection. So this is one of my personal favorite attacks. It's actually really, really cool. So the idea behind fault injection is that chips have very strict operating conditions. So if you've ever done PCB design or made a PCB for some chip, you'll know that they have these really, really annoying things called data sheets. And so the data sheet is going to tell you exactly what operating conditions the chip is designed to handle. So in this case, this is the ST Microelectronics STM32, which is this board right here, this one. And we can see that there's a large number of restrictions on the voltages you can supply to this chip and the temperatures it can operate at, things like that. So I want to point out right here, actually, you can see just to give you an example of how precise these tolerances can be. The minimum voltage is 1.08, typical is 1.14, and max is 1.20. So the way that we designers will actually make these voltages consistent is with the use of things called bypass capacitors. So you can use capacitors to filter out noisy voltage lines, keep things nice and stable and nice and even. And so the idea here is that since these chips are so sensitive to these components, these input parameters, if we can just intentionally bring the chip outside of its standard operating conditions briefly, we can hopefully break the chip. So let's look at voltage as an example. So for voltage on a chip, what you'd like to see is a totally flat line. So if the chip says 5 volts, you give it exactly 5 volts throughout all the time, right? But if we're malicious and we want to do some type of fault injection, what we could do is start out, boot the chip normally, keep it nice and flat, and then at the exact right moment in time, briefly cut the voltage down to 0, and then bring it back up again. Now, why does it have to be brief? Well, if you bring the voltage down to 0 and just keep it there, the chip's just going to turn off. So the idea is we want to inject these faults for a very short amount of time, so that we don't break the chip completely, we don't reset it, but we push it into this weird kind of undetermined state. Does that make sense? And so again, just to be very specific, what we want to do is cut the power at the exact right time to make something go wrong with the chip. And so here's kind of your general overview of what this fault injection might look like. So we have the expected input. You can imagine this is your voltage or a clock signal. And we have a multiplexer that lets you select whether we're choosing the expected input or some malicious one. And we bring that to the device under test. And so for most of the time, you'll be running this expected input, just pass that right through to the device. When the time comes, you can actually switch briefly to the malicious inputs and then switch back to the expected input. So, everyone make sense? That's kind of the game plan here. So who's ever programmed an Arduino before? Okay, great, plenty of people. That's awesome. So Arduino Unos, these are these little blue boards you might have seen around. And so these are a great, if you've never programmed one, by the way, they're really fun. So they're called microcontroller. They're a great way to learn embedded electronics. And so the Arduino Uno is going to be the target of our attack today. So we're going to do some fault injection on an Arduino. And specifically what we're going to try to target is the crystal oscillator. So this chip right here is a special crystal that's designed to resonate at 16 megahertz. That's going to provide a very stable clock signal to the Arduino. So it uses this as a reference to know how fast this clock should run. And so let's talk a little bit about how the clock signal works. So on the datasheet, which we'll show you in just a second, you have the oscillator attached to two capacitors that are then loaded to ground. And so the way I want you to think about this is like a plank, like some type of wooden plank on two springs that kind of bounces up and down. So you can see it bounces up and down. And we'll show on the oscilloscope what that looks like in just a minute, but the oscillator just kind of has this resonant frequency. It looks just like this, goes up and down at a regular frequency. And this is used by the Arduino as an input to understand how to generate its clocks. Everyone clear on clocks? So how does it actually look like on the circuit? So this is the input to the Arduino. This is actually from the reference design. We have that crystal right here, and those two capacitors that load the crystal down to ground right here. And so what we're going to do is attach a wire to this point of the chip, which you're not supposed to do. This is a very bad thing, but we're doing bad things, so this is actually good. And what we're going to do is very momentarily short that pin out completely to ground through a transistor. And we're going to do it in a way that's been pre-profiled to make it so that we don't completely kill the chip, but we just bring it into this weird condition. And so here's an overview of what the setup actually looks like. So here's the Uno board, and I don't know if you guys have used Unos before. What you can actually do is pop the chip out. So normally this is where your processor would sit. What I've done is I've taken the chip out of the board and put it into a separate breadboard. Now why would I do that? Well, this way we get access to all the pins. So we can do weird things like inject faults to the clock, which you're not supposed to do. So we have the microcontroller just taken out, but it's still an Arduino. This chip has been removed, and all the pins that you need to power the chip are connected. So we have power coming in, we have serial coming in, everything. So it works just like an Arduino, but the chip has been taken out. So don't worry about that too much. The chip has just been taken out so we can mess with the signals. And then what we have is we have these two pins that go to the oscillator, which is on the board, and the second pin to the oscillator is attached to this transistor. So this transistor is driven by an STM32, which is a very, very fast microcontroller. It's actually so fast that we can inject these tiny spikes way faster than the Arduino is able to handle. And so this is what's going to control our injection, and this is the transistor that will determine when it's active. So when we send a 1 to the transistor, it'll short the clock out. When we send a 0, it'll just let the clock pass through normally. Any questions on the setup? So let's take a look at some photos of the setup. So like I said, this is normally where the chip goes. We've taken it completely out of the board and just put it over here. But don't worry, it's still an Arduino. It still works the same way. And we've taken the jumper wires to connect the chip in the exact spot that it needs to be connected. And here we have those two oscillator pins. And so you can see I've taken a line out from the oscillator pin into the transistor. And we have this other wire that goes to the attacker board. And it goes right here into the STM32. And so what's running on the Arduino? Well, the Arduino is going to run a special program that I've written that simply does while true, print we are currently locked. And then after the while true loop completes, which it will never, ever, ever complete, it will print out the flag. So if we can find a way to break this while true loop and skip out of the loop to print the flag, we would be able to change the control flow of the program. So note, obviously there's no way for us to do this without some type of weird microarchitectural attack. Like this is never going to break. This loop will never break at the ISA level. So any questions on what the loop's doing? And so what we're going to do is we're going to try to inject a fault right here at the while true part to skip this condition and make it false, and then fall through into the print statement. So demo number 2, what happens if we intentionally violate the chip's expected operating conditions? So I'm going to go ahead and start by plugging into the Arduino, and we'll see what it's sending over serial. And then we're going to use the oscilloscope to see what the clock looks like. All right, so we're connected to the chip, and we can see it boots up, and it just keeps printing, we're locked, whatever. And so you can let this run for all time, it will never break the loop. So let's go ahead and switch over to the oscilloscope and see what that clock signal looks like. So here we are in the scope, and I'm going to go ahead and connect into the clock pin. So let's see if we can observe what's going on. So you should be able to see there's some type of fluctuation happening. Bring this up. And we'll go ahead and set a trigger here so we can try to capture that and zoom in. And you can see we have a beautiful, stable clock. And if you look at the frequency at the top, it's roughly 16 megahertz. So this is wonderful. We're attached to the oscilloscope. It's oscillating and resonating its natural frequency. We have a beautiful 16 megahertz or so clock signal. So let's see what happens when I connect the attacker board and inject some faults. So let's watch the clock signal first, and then we'll take a look and see if we can succeed. All right, so you can see that did something. It has decreased the amplitude just a little bit, but it's still running at a nice frequency. And let's go ahead and inject the fault. So I'll go ahead and prime our board here. And when we go ahead and inject the fault, you'll see it just starts like kind of glitching out. So let's get a better view of that. We'll zoom out a bit, and we'll set a trigger up here. And so you can see this is what a fault looks like. I didn't actually capture enough. Do it again. And so we go from this very nice, normal clock in some normal voltage range to just shooting up to a massive voltage. Because we bring it up to VCC. I might have said ground earlier. I meant to say VCC. And we just keep it kind of stuck at this very high voltage for a good amount of time before letting it go back to its normal value. So any questions on what's happening? We're just messing with the clock and making it do weird things. All right, so let's see what happens. I'll leave this running. So let's see what happens when we go ahead and reattach the serial, see if we can observe some strange behavior.
So I thought the plan was to keep the voltage down for a little while and not shoot it up.
Up or down, it doesn't matter.
Oh, but it's still oscillating.
Yeah, it still oscillates, but it's outside of the voltage range for what the clock's supposed to be. Okay. So the internal generators, because this is not the actual clock signal, this is used to create the clock signal.
Makes sense.
So by spiking it up, it just freaks out the clock. So, and we'll define what I mean by freaks out in just a minute. So let's reattach here, and we'll see we boot up, and we'll go ahead and inject that pulse. So 5, 4, 3, 2, 1, and we did it. So we broke the loop. So we have just successfully, you can see we had some strange serial printing out of some weird nonsense, and then we were able to break the loop. So we did it. We completely changed the control flow. just by injecting some pulses into the clock signal on the chip. Pretty cool, huh? So that's fault injection. So how can you do fault injection if you want to try and do it yourself? Well, there's a ton of different ways to do this, actually. There's plenty of different tools you can use. So you can use things that are very cheap, like a grill lighter, which, believe it or not, actually does work as a fault injection tool. You can use things that are affordable, like we just did here with an oscilloscope and some bench tools. And if you want to get crazy expensive, you can do the really cool stuff. But yes, a grill lighter will work for fault injection. So if you take the piezoelectric crystal out of the grill lighter and you send it a voltage pulse, it will induce an EMF into the chip that's actually able to induce faults. So it really does work. You can try this if you want. Yeah, so barbecue lighter, fault injection. You can also use more advanced electromagnetic signals or photonic signals as well. So here's a image from an applied science article showing some more examples of fault injections. You can have kind of really cool benchtop things where you have this precise ability to inject. So if you want to know more about that, talk to Vincent. His lab used to do a lot of that. So a couple little examples of fault injection. If you're bored and want to watch some YouTube, two great videos I highly recommend. The first is from Thomas Roth, Stack Smashing, where he was able to hack the Apple AirTags within a couple weeks of them launching. It was a super cool video. So he actually uses this technique to break into the NRF microcontroller on the AirTags. And then Joe Grend, who's another famous hacker, one of the biggest legends in the field, he was able to recover $2 million from a hardware wallet using fault injection. So it's a real technique. People really do use it. And the question is, why does it work? I mean, you'd imagine it's almost like magic, right? We just send some weird signal to the clock and all of a sudden we instantly get access to the flag or we break the loop. Like that doesn't make sense. That should be sending off alarm bells. Why does that work? Well, if we go back and revisit our digital logic from 6004, you have to remember how are digital signals represented in an analog world. Remember, we're in the analog world today. And so if you think about it, we have a choice here, right? We have a full spectrum of voltages from 0 to up to VCC, we'll call it 5 volts. We can choose which parts of this region to represent as a 1 or a 0. And so a very naive choice would be to simply draw a threshold. Draw a line here and say anything to the left of the line is a 0, anything to the right is a 1. Just draw that line in the sand and just be done with it. The problem is, real chips are noisy. And so doing this very clean threshold is actually problematic. So what we really want is a region where it's not exactly defined, not precisely defined. And so a 0 is to the left of this undefined region, a 1 is to the right of the undefined region, and in the middle it's just, we don't have a definition. So I want you to remember this is how 1s and 0s are represented inside of the chip. So another thing is that real world circuits take time. Unfortunately, they're not instantaneous. And so let's just revisit really quickly the ideas of propagation and contamination delay for 004. So here we have an example inverter. So A goes through an inverter and becomes B, 0 goes to 1, 1 goes to 0. And up here we have a timing diagram. So we show A goes to 0 to 1. And there's actually a little bit of time where B is switching from 1 to 0. And so we call this region here the propagation delay from when A begins to switch to when B's value is stable. That's the propagation delay. So the entire combinatorial path from start to finish, and that's our propagation delay. And our contamination delay is when B is still stable at that old value. So that's this little region right here. Make sense? Propagation and contamination delay. So let's talk about flip-flops. So a flop, if you'll remember, has a clock, a D input, and a Q output. And so the idea with flops is we actually have a couple constraints we have to make for that data on the input latch to be latched correctly at the clock pulse. So with a flop, the clock goes from 0 to 1, and at that time, the data input is sampled and becomes the new output. But for that to really work properly, you have to meet a couple conditions. So the input D needs to be stable around the rising edge of the clock to not induce what's called metastability. And so there's two conditions that we need to meet for this data input. The first is that we hold the data for what's called setup time. So the data is stable up until the edge of the clock for some setup period. And the data has to hold for at least some certain amount of time after the edge of the rising clock. So these are two very important things in circuit design. And designers spend a lot of time and money making sure that their chip will hold under these conditions for a given clock frequency. And so if you were to somehow violate these conditions, you would induce metastability. And that will load a contaminated value into the register. So what does metastability look like? This is a screenshot from Colin O'Flynn's excellent book, The Hardware Hacking Handbook, which actually you all have access to through O'Reilly. So I highly recommend checking it out. It's an excellent book. And you can see here, when the clock goes from 0 to 1, if the clock comes too soon or we don't violate the setup or hold times, we just kind of do whatever. Metastability is induced and you have no idea if it's going to be a 0 or 1. So that's what happens when you mess these up. And so let's take an example of some sequential timing. So here we have two flip-flops. D1 goes into Q1. We go through some combinatorial logic, pass through this cloud of combinatorial logic, becomes D2, and it gets latched at the end of flop 2. And so let's look at what happens in detail from one period of the clock. So the first thing that happens when the clock switches, we have a propagation delay through the first flop, where there's some time for the data to become stable at the output of the flop. Then we pass through the combinatorial logic, finally arriving at the input to the second flop. And now we need to make sure that this input is stable for the entire period of setup. So this needs to be ready not at the clock edge, but actually before the clock edge for that setup time in order for flop 2 to read the value properly. And so this will actually determine your critical path in your system. So the longest path between two flops through some combinatorial delay is going to be the limit how fast you can run your clock at. And so what happens in a fault injection scenario? Well, what will happen is we can actually, what happens if the clock comes earlier? So what you saw here, we were adjusting the clock by inputting these spikes and these pulses. What you can think about happening is inside of the clock generator, it's injecting these pulses that happen outside of the regular frequencies. And so what that does is effectively moves the clock pulse earlier into that setup region, violating that setup constraint. And so now the data could be changing because we have not finished propagating the logic correctly, but we hit a clock pulse anyways. And so we can latch just any value at all. It's just completely random. We're in metastability. But what happens about voltage? So earlier we said that you could also do this with voltage glitching. Well, decreasing the voltage, if you remember, will actually increase the propagation delay. There's less power in the system to force data through. And so what that has the effect of is bringing these propagation delays up to the clock. Again, hitting that period where we're not hitting setup time. We're inducing metastability once again. And there's one more case, which is hold time. So for sequential circuit again, once the data has been latched properly at data 2, it needs to be constant for the hold period of flop 2. Otherwise, we again hit metastability. And the way we hit that is through the sum of the contamination delays of flop 1 and in the computational logic. And if we are unfortunate enough to increase the voltage, we will actually decrease the propagation time. So more voltage means the chip runs faster, and actually these values will shrink and be brought into the hold time. So we violate hold time, and once again we hit metastability. So voltage up is bad, voltage down is bad, clock too soon is bad. Any questions? So we hit this metastability, and then what just happened in the Arduino, we had metastability throughout the whole chip. Clearly that meant the serial ports gave us some weird data, but it also broke the loop. So we were able to break out of the loop and see the flag. Yeah, so it brings it forward, we break hold time. So can we stop it? Oh yeah, what's up?
What's the effect of changing the voltage again?
Increasing the voltage will decrease propagation time.
Okay, but if the circuit has error correction and like shifts the voltages into 5 and 0, if error happens, then why does this happen?
What happen?
You said it increases the propagation time, right?
Right. No, decreases.
Decreases the propagation time, but why does it happen?
Why does it happen?
Yeah.
Oh, that's a digital IC design concept. So more voltage, we'll talk about capacitance later, but the reason chips take time to switch is because there are capacitive loads everywhere in the chip. They're called parasitic capacitances. So more voltage, you can think there's just more power available to just quickly switch those capacitive loads. Yeah.
Why doesn't this sort of change like the clock cycle, like damage, or like prevent other parts of like the Arduino to work? Like here it's like everything except like we can just get the thing we want. Then like other parts of the Arduino are working properly. Like that's kind of surprising.
It's very. You should absolutely be surprised. Yes. The reason it works so well is because I spent a lot of time profiling it to make sure the pulses that the STM injects are like really perfect. And this is where the art of fault injection comes into play. So if you want to do something like break a bootloader, you'd have to actually begin the chip at a certain time and then inject the fault at a certain time. So not just press a button, but wait a certain amount of time. Yes?
So you have to optimize your glitch width as well, right?
Yes.
As well as the timing?
Yeah. Yeah, so that's why we're using STM instead of just a button, is if you saw in the oscilloscope, the pulse widths were carefully chosen to not break the chip. Yes?
I guess this might sort of come into this, but like, are there sort of, I know there's sort of built-in mechanisms that prevent clock skew in a lot of chips, but can that sort of prevent this attack if not done well, or will that not sort of?
Yeah, I mean, I'm not entirely familiar. It depends on the mitigation. There definitely are architectures out there designed to mitigate this. So Atmega is not one of them. It's very easy to do this on an Atmega. More advanced chips might be harder. Yeah.
So presumably you have to do a lot of iteration to like figure out like the parameters of your injection. Like, does this ever cause problems where like you do permanent damage to the chip body?
Oh yeah. We've seen it. This is the result of many. Actually, when I did this demo, I was just hoping it wouldn't fry the memory. But I've had these examples where the chip memory was just gone. So we had to reflash it and stuff. Actually, I think one time it was broken so bad we had to reflash the bootloader. Yes?
How could you use an attack like this to like get information from the chip? Because here, like you preloaded it with something where okay, it's gonna glitch and then we'll see this last line. But how could you use it for something that like already has its own firmware or software on it to like get information?
Excellent question. So the question, in case you didn't hear, was how can you use this in a real scenario to really get information leakage? Quintessential example is your bootloader is locked from letting you use JTAG. So you can't get a debug port, it's like firmware locked. Usually there's some part of the initialization boot ROM that'll read the register or the fuse value to see are we locked or not. And if you can glitch that exact moment, it can sometimes switch it into the state where it's not locked. So go watch Thomas Roth's video on the AirTags.
I can also add a little bit to just relate to the last lecture. So remember in the last lecture we talked about secure boot. So you need to match whether the hash of your the boot procedure matches a pre-compute hash, and you can imagine that comparison. You see it's an if condition. If you glitch that point, then even if the hash does not match, you can go to the wrong branch and you assume the hash matches. So something like that will be able to, the fault injection can be useful in this case. But of course, you time it very perfectly to glitch the specific point when you compare the hashes.
Does that make sense? Anything else? That's pretty sweet, right? So, mitigations. How do we stop it? There's two that are very simple mitigations we can think about. The first is redundancy. So the reason this happens is because the chip did the wrong thing, quote unquote. So if you had two copies of the core running at the same time, it's likely that the faults you induce in one core are not going to be the exact same in the other. And so you can have another version of the core that's checking itself. But this is very expensive. You have a lot of duplicated silicon, you're wasting area. So an example of this would be the Google OpenTitan project, which, are they coming to talk this year?
Not this year.
Okay. Well, OpenTitan's very cool, so look them up. They're a great project. They do some very cool things. The other thing you can do is non-determinism. So for those examples we talked about, where you're verifying the hash of some boot ROM, or you're checking your fuse state to see if you're locked or not, you'd have to know exactly when to inject the pulse. So if you have this non-determinism, this randomness added, you're able to actually reduce the attack's accuracy. So now it just makes my life as the attacker way harder. It's already pretty hard as it is, so this just makes it even worse. So those are some example mitigations you might want to think about. So that's fault injection. We got 2 more to go. So now let's move on to timing analysis. So I want to play a game with you guys really quick. We're going to play a game here called Spot the Bug. So I have a memory comparison operation that's designed to check 2 buffers to see if they're equal. Who sees the bug? Yeah.
Basically, if the buffers don't match, it'll return quicker than it will if the buffers do match, and so you can analyze how long that takes to determine what.
Yes. What was your name, by the way?
Sam.
Right on. So I don't know if it might take you guys a second to catch up. Sam, I think that was the fastest answer we've ever had for this question.
We did it in one of the previous lectures.
Oh, did we? Okay, never mind then. Sorry. It's not bad. Well, you guys already know what this is then, so I don't even need to continue. So that's the bug. Sam is completely correct. So that's the problem. Returns too early. And so instead of a demo, we're actually going to let you guys do the demo on Wednesday. This week. Oh yeah, I should say this week. So come back this week. Come back on Wednesday. Bring your laptops. Bring a USB cable if you've got it. So the ability to connect to USB for your laptop. So if it's a Mac, have your adapters ready. And you're going to do this attack yourselves on some real chips. So timing analysis, to be continued. Lastly, we have power analysis. So this one is really cool. So power analysis is another passive attack where we're going to try to learn what the chip is doing by watching how much power it's consuming. So what is power? Well, power is simply voltage times current. And so the idea here is we have a power supply of some kind. This is like a battery or a USB or whatever, and it's going to drive this device in our test. And we'd like to know how much power is the device using at a given time. And so the way we're going to do that is by learning how much current is being sourced or sunk through the device. So if the device is pulling more current, it's using more power. Pulling less current, it's using less power. Because that voltage is pretty much a constant. So power, voltage times current, but voltage is a constant, so we want to know what's the current. Make sense? There's a big problem with this. How do you measure current on an oscilloscope? The problem is an oscilloscope is designed for measuring voltages, not currents. So we're going to do a little bit of a trick here, which is to throw in what we call a shunt resistor. And so this shunt resistor is going to be placed in series with the whole device under test. So every single amp of current that flows through the device has to also pass through this shunt resistor. And so the current's going to pass through just like before, but now there's going to be a slight voltage drop across this resistor, which we can measure. So let's actually do that calculation here really quick on the board. So if we have a power supply, let's say it's a 1 volt supply, just keep things simple. We have a shunt resistor, we'll call it 1 ohm. And we have a device here. We have some current passing through, and this current is going to be equivalent to whatever the device uses because it's all going through in series. And so using Ohm's law, V equals IR, 1 volt equals current times 1 ohm, and we can infer the current is 1 amp in this situation. So by measuring voltages, we can learn what the current is. Does that make sense? Cool. So we're going to apply Ohm's law. Again, V equals IR, I equals V over R. We measure the voltage, we know what the shunt resistor is, we can learn the current. So this is how we're going to do this attack. We're going to do the same thing as before. Take the microcontroller out of the chip, throw it at a breadboard, so we can do this probing stuff. Again, it's still Arduino, still works the same way. We've just taken the chip out and we put it here. Then what we're going to, oh yeah, question.
If there's a voltage drop between the voltage source and the device under test, then couldn't you run into the problem where the voltage is lower for the device under test than it's expected to be, and then everything runs slower, etc., so you're not getting like the exact behavior that you would expect without the shunt resistor?
That was an excellent question. So the question, what was your name by the way?
Shruti?
Excellent question. So the question was, what happens if you have a shunt resistor? Yeah, you're going to have some voltage drop between the source and the device. So the answer here is, for us, it doesn't really matter. It still is able to work. You want to select your shunt resistor so it's a very small resistance, so it's not a huge voltage drop. But if you were to do this for like a real chip that's very sensitive, you'd probably want some bypass caps on the other side and probably maybe increase your voltage just a little bit to compensate. But yeah, excellent question. So the answer is it kind of depends, but for this setup, it works. And so here's our shunt resistor. We're going to measure the voltage drop across this resistor. And so for us, we're going to use 50 ohms. Relatively small value, but not insignificant. But again, for us, it's still able to work. And we're going to go ahead and measure that and see the power analysis. And so the victim of our attack today is going to be RSA. So here on the right, I have broken out a little bit of what RSA is going to do internally. And on the left, we have a trace I collected on the scope beforehand. And so what I want to do is walk through with you the algorithm here, show you how to learn what RSA is doing from power traces, and then we're going to do it for real on the scope and see if we can, as a class together, learn what the secret key is that I've embedded in this processor that you don't know. So, modular exponentiation is a very crucial part of RSA. The idea here is we're going to do this modular explanation problem, and there's a little bit of branch divergence that's based on the secret here. So the secret value is E. E is one of the arguments here. And we're going to go bit by bit and look at each bit of E. If there's a 0 in the least significant place, we're going to call mod mult 1 time. If it's a 1, we're going to call mod mult 2 times. Does that make sense? And then we're going to shift and do it again. So for every bit, if it's a 1, we call mod mult twice. If it's a 0, we call mod mult once. So let's walk through and take a look at this. So here I've run a low-pass filter over the power trace to just make it a little easier to see. And again, if E is a 1, we're going to call mod mult twice. And otherwise it's going to be once. So here, these spikes are the loop overhead. So this is shifting E and also checking to see if E is non-zero. Then, if we have 1 call to mod mult, we'll have a very brief moment of power usage between those loop overheads. So it's a kind of a shorter call because we only called mod mult 1 time, it takes less time. And then if we call mod mult twice, as it would be for a 1 case, it would be a longer gap between those spikes. And so for this example, E is hex F0. It's read backwards, but it's F0 because there's 4 1s here, 4 zeros here. With me? So that's how we can learn the secret exponent for modular exponentiation. So now it's time for demo number 4. We're going to find out what happens if we watch the chip's current draw. This is still running, wow. All right, so let's switch back to the scope here. I'm going to go ahead and reset it. And I'm going to go ahead and boot up the Arduino. So now we are attached to the power line. You can see there's very little fluctuation because it's a very tiny difference here. So we're going to go ahead and zoom in and see if we can capture something. And so what the chip is doing is every 100 milliseconds, it's going to compute RSA and then shut itself down. So there'll be some noise and then it'll be stopping. Or some signal and then it'll stop itself. So we should be able to see the signal pretty clearly. So we're looking at the power trace. Let's see if we can catch a signal here. So you can see we got like some noise and then every once in a while we see a little bit of a pulse come through. Let's see if we can zoom in on that. Okay, so we caught something. It's a little bit hard to read, but let's see if we can make out what it's doing. Actually, I don't like that one. We'll catch another one. Yeah, that's nice. Okay, we'll use this one. So let's see if we can read out together what the RSA is doing. Is it easy to see? Is it a little hard to see? Turn the lights off. Can you guys read that? All right, I'll tell you guys the first one. So right here, this is a 1. The signal here is a 1. So what is this next signal? Call it out. 0, okay. I'll write these down. We have a 1, a 0. What's the next one? 1. Next? 0. Next?
1.
Next?
0.
0.
1 0.
1 0. Correct. So this was the key. It's just alternating 1s and 0s back and forth. This is the private key. So we did it. We were able to learn the RSA modular exponent just from looking at the power traces. Pretty cool, huh?
But isn't the longer one supposed to correspond to 1s? Because there we are doing twice multiplication, 2 multiplication.
Oh, I might have screwed it up. This is a 0 here. That's what I meant to say. Did I say 1?
Yeah.
All right, so it's the opposite of whatever we said. But yeah, this is a 0 here. That's a 1. So more or less we got it right. You just throw it under next door. It's all good. So yeah, that's modular exponentiation. So the idea here is, again, with a couple minutes of setup on the bench, we didn't really do anything super precise. We were able to see exactly what the chip's doing. Okay, so why does that work? Well, if you think about a CMOS chip, so this is your quintessential CMOS inverter. You have an input, and then you have your complementary MOS transistors, and then this is what I was talking about earlier, that capacitive load. So whenever you're switching a capacitor or any type of CMOS circuit, there's always a capacitive load that you kind of have to draw. And so that could be charging the capacitor or discharging it, but this is what makes circuits take time, right? You have to charge and discharge this parasitic capacitance. And so switching from a 0 to a 1 or a 1 down to a 0 requires either charging or discharging this capacitor. You have to do it. That is a law of physics. And so that'll consume power. So the more capacitors you're switching, the more switching power is going to increase in that instant, right? And so different parts of the chip are going to use different amounts of power. So by looking and seeing how the power varies over time, you can learn high-level information about the chip's utilization over time. So that's what we were able to do with that simple power example. So the key takeaway, different parts of the chip are active depending on what the program is doing. I said the word program twice, it's that important. and watch the power consumption over time to learn what parts are active at what time. Does that make sense? Cool. So that's all I got for you today. Hopefully that was kind of fun and insightful. We love doing these demos, they're kind of fun. If you have more questions about these, please come to office hours or shoot me an email, and I'm more than happy to sit down and show you some more stuff in detail, or some other cool toys we have in the lab. But next is your turn. So next week, or not next week, on Wednesday, we're going to be doing the physical attacks recitation, which is people every year, everyone says this is one of the most cool classes that they do. So I hope you guys enjoy it. We spend a lot of time on it. The rules are very simple. There's one rule, which is please try not to break the chips. If you do break the chips, it's okay. Just try not to. But anything is fair game. Do whatever you want. It's a lot of fun. And so what I'd like you to do is, if you can, bring a USB micro or a USB-C cable. If you've got one, bring it. We have some for you as well, but it's better if people bring their own. And also go ahead and install the Arduino IDE if you have yet to do so. So we have instructions. We're going to post them on Piazza. Go ahead and just do that before you come to class so you can hit the ground running. Cool?
Really appreciate Joseph for the great lecture, and if you really want to see more things, there are things on the table, so feel free to stay a bit longer. Anyway, we are early today, so I don't think it's like very, so that if you are curious, just take a look.
Yeah, if you have questions, just let me know.
Yes.